let us know.
Okay. Good morning. My name is Ryan Trey Van Haren. I'm an undergraduate student with the Arizona State University Department of Physics. And today I'll be presenting the effects of crystal orientation upon surface energy of native oxides on Si, silicon 100, and silicon 111 as measured by three-liquid contact angle analysis, 3LCAA. So I intend to begin by defining surface energy, followed by our motivation for measuring surface energy and its possible applications. I'll present the hypothesis that we set up to test with our experiment, and describe our primary measurement tool, 3LCAA, three-liquid contact angle analysis, and explain its usefulness. Our results will allow us to answer the question if hydrophilicity can be measured by surface energy, and how surface energy and surface atomic density correlate. To understand surface energy, we have to understand that it is quantified by the sum of all interaction energies on the surface of a given material. This illustration here on the bottom left demonstrates a silicon carbide crystal here interacting with water molecules above it. We can ask if the interaction energy scales with the surface atomic density of the crystal. To test this correlation, we can, by testing this correlation, we can answer the question if we can measure hydrophilicity quantitatively by 3LCAA. This illustration here in the bottom right is a good illustration of our silicon 100 crystal with our surface atoms demonstrated by these orange atoms here. So now we can state our testable hypothesis that if the surface atomic density is increased, then the surface energy will also increase. So what is the motivation for measuring surface energy? A knowledge of the surface energy of a material would allow for the creation of superior hermetic, meaning airtight seals, via the nanobonding process. The nanobonding process adheres two materials together through the molecular interactions between individual atoms on the surface of the two materials. This image in the middle here shows how native oxides, shown here, grown on the surface of a silicon dioxide crystal, bond to this ordered precursor phase that we can grow on another surface. The surface energy of a material scales with the surface roughness of the native oxides that grow on the surface, these native oxides here. The surface roughness corresponds to the number of defects, dangling bonds, and impurities in the native oxides. The presence of these defects negatively impacts hermetic seals by allowing for fluid percolation and ion diffusion when they are exposed to saline environments. For this reason, hermetically sealed electronic sensors must be replaced after a relatively short period of time. For example, glucose sensors only last about a week in the human body. If we could improve the hermetic seals in these electronic sensors, we could drastically increase the lifespan and reliability of these sensors without significantly increasing the cost or altering the means of production. We measured the surface energy of these materials via the three-liquid contact angle analysis method. The liquid contact angle is defined as the angle that the tangent line to the surface of the droplet makes with the plane of the material here. So here is our surface contact angle. These two images here on the right show a hydrophilic surface. And this image here is an example of the type of droplet that we analyzed during our results. So how does 3LCAA tell us about the hydrophilicity or hydrophobicity of a surface? How hydrophobic or hydrophilic a surface is directly related to the surface energy of the material. We are able to use 3LCAA combined with the Cecil drop method to refine our measurement of the contact angle, where by using these two methods combined, we're able to get a variance typically less than 5%. Water droplets placed on a hydrophobic surface tend to take a more rounded shape, as is shown here in the bottom left, while droplets placed on a hydrophilic surface tend to take a more flattened shape. This is due to the There's work required to flatten out these droplets from an idealized spherical shape, and this energy is drawn from the surface energy of the material. So in this way, we see that hydrophobic surfaces tend to have a lower surface energy, and this results in a rounded droplet, while hydrophilic surfaces tend to, or have larger energies, and this results in a much more flattened droplet. So in this way, 3LCAA allows us to measure both the surface energy of a material and the hydrophilicity of that material. So how does measurement of the liquid contact angle result in a value of surface energy? Young's equation, described here in this red box, allows us to connect our measured surface angle, or contact angle, to the surface energy of the material. Van Alst's theory, with a mathematical representation shown here in the green box, allows us to further split the surface energy into three distinct energy components. These are the Lipschitz-Van der Waals energy, shown here, which is the energy of interactions of individual atoms on the surface of both materials. The electron donor energy, which is shown here as gamma plus, which is the interaction energy between of the electron donor interactions, and gamma minus, which is the energy of electron acceptor interactions on the surface. We can combine these two equations to get the Young-Dupree equation, which allows us to directly relate our measured contact angle to our three components of surface energy. So what is the difference in surface atomic density between silicon 100 and silicon 111? We can see in this first image our orientation of the silicon 100 crystal. And we can see that the corresponding vector is normal to the face of the cubic silicon crystal. In this orientation, silicon has a surface atomic density about 6.78 times 10 to the 14 atoms per centimeter squared. We can see down here that silicon 111 has a very different orientation. We can see that the corresponding vector is normal to the diagonal cross-section of the cubic silicon crystal. And we can see that this orientation gives us a very different surface atomic density of about 7.8 times 10 to the 14 atoms per centimeter squared, which is about 15% larger than that of silicon 100. When we perform 3LCAA to measure surface energy, we're actually measuring the energy of the surface of the native oxides that are grown on the surface of the silicon wafer. These native oxides grow naturally on the surface of a silicon wafer when it is exposed to an oxygenated environment, such as normal air. These native oxides are typically not very thick, only about 10 to 20 angstroms. And this illustration is good for seeing the structural disorder in the native oxides and the surface roughness. So how do we set up our experiment to test our hypothesis? Our experiment was conducted in a class 100 hood with proper PPE and well-cleaned equipment. You can see here on the top right an image of our silicon wafer with our droplets placed upon it and our camera for recording these results. Down here is an image of myself and a couple of my co-authors who happen to be here as well, conducting 3LCA under our class 100 hood with our proper PPE. We use 5 to 6 droplets per wafer, per liquid, in order to get many results to further refine our measurement. And we use the volume of these droplets is only a few microliters in volume in order to reduce the effects of gravity flattening out our droplet. We also take these pictures very quickly after the droplets are placed in order to reduce the effects of evaporation. We also use 3 very different liquids for our analysis. We use water, glycerin, and alpha-bromonaphthalene. And this is because they each have very unique characteristics and they give us very distinct values for the contact angle. These 3 liquids are also very useful because their surface energy is very well understood, and because by using these 3, we evaluate two polar liquids and one non-polar liquid. Water and glycerin are both polar, while alpha-bromonaphthalene is non-polar. So presented in this table is a collection of our calculated results. We can see here in this first column is our measured surface energy for our silicon wafers. We see that the average surface energy of silicon 100 is about 50.6 millijoules per meter squared, while the surface energy of our silicon 111 crystals is about 56.7 millijoules per meter squared. If we look at the relative difference between these, we can see that there is a difference in energy about 12%. So the surface energy of silicon 111 is about 12% larger than that of silicon 100. This also matches up with our difference in surface density. So here we have a graph of our results with our standard deviations. You can see that our standard deviations are very small. We can also see from this graph that our surface energy of our silicon 111 is much higher than our silicon 100 crystal. So we can gather from this that silicon 111 is more hydrophilic than silicon 100. So to conclude our results, we know beforehand that silicon 111 is about 15% more dense at the surface than silicon 100. We were able to measure by 3LCA, the surface energy of both of these crystal orientations, where we find that the surface energy of silicon 111 is about 12% larger than that of silicon 100. We also know from previous experiments that hydrophilicity scales with surface energy. So this allows us to confidently conclude that surface energy and hydrophilicity scale with surface atomic density, and that hydrophilicity can be measured quantitatively by surface energy and via 3LCAA analysis. I would like to thank Arizona State University Department of Physics and my co-authors. Thank you very much.
We have time for one question.
So how does the volume of the drop? Because it looked like your different fluids were all different volumes.
They were.
So how does the volume of the drop affect the contact angle?
Well, the larger the drop, the more it tends to flatten out due to gravity. If we can keep it very small, then the surface energy that wants to pull together into a spherical shape dominates in that situation. But the larger the drop we make, the more gravity tends to flatten out that drop, and so that affects our contact angle and gives us a skewed value for the surface energy.
And I have a question. So finally, that nanobonding is what? Is just dispersive forces or covalent bonding? So what's that?
It's mostly due to the Lifshitz van der Waals energy interactions. So it's the interaction between
forces.
Right, individual atoms themselves on the surface.
Okay, let's send speaker again.